So we will work over the field Q of rational functions in two variables. T, well, in fact, both are well known to us, but now they will appear simultaneously. And then we'll have lambda f, which is just the base change to this bigger field. So it's an infinite dimensional vector space over this field. And we introduce two parameter deformation of our favorite z lambda, centralizer order. So this is the usual integer z lambda times the product over all parts of this partition, 1 minus q to lambda I over 1 minus t to lambda I. So in particular, if q equals t, then we get just non-deformed old z lambda, positive integer. And this will be used at some point. So we introduce scalar product. Where p power sums form an orthogonal base. It's symmetric, so it's p nu p lambda, and is delta lambda mu. Yes. F is this field. Rational functions in Q and T. Pardon me? Yes. So it's orthogonal base with such length. Okay. And note that if we invert Q and T, then z lambda will be equal to q inverse t to the power size of lambda, z lambda of qt. And this implies that if you consider the scalar product with respect to, yeah, maybe I should introduce this index because it will depend qt on this product depending on qt. Will be q t inverse to the power of lambda, of total size of lambda, fg u inverse t inverse for what I'm saying. Maybe I should say n for f and for degree f equal to n. What's the question? Sorry, yes, sorry. So we introduce this scalar product in the base of power sums. So we require this base to be orthogonal, and well, the length is given by z lambda. Okay. And what's the issue? Yes, by definition. So we consider the symmetric bilinear form, non-degenerate. Okay, so one more useful notation. It's called Pochhammer symbol. Well, infinite symbol. Given a number a and a parameter q, then this symbol is the product of 1 minus a q to the r. Pochhammer. Да. Okay, and we set some infinite product of infinitely many variables x, infinitely, well, maybe I should write x, y, and it depends on q and t, and this is the product over all I, j, indices of x and y variables, t, x, I, y, j, Pochhammer symbol over the Pochhammer symbol over x, I, y, j, q, infinity. Yes? Yes, it's the product like this. It's very similar to how we defined something for Holder-Wood polynomials. You will see momentarily. Yes. X is x1, x2, x3, and so on. And similarly, y is y1, y2, y3. So we have two groups of infinitely many variables. And this is a symmetric function in x and symmetric in y. Right? So we're just deforming the usual scalar product in some funny way. And then the first lemma says that this guy, this infinite product, equals the sum over all lambda, z lambda of qt inverse, p lambda of x, p lambda of y. Okay, and the proof was given one time in the winter, also just 1 week ago, right here at this blackboard. Let me repeat it for the third time. So we consider the logarithm of this infinite product. And this logarithm is the sum over I and j, the sum over r, logarithm of 1 minus q to the r t xi yj minus logarithm of 1 minus q to the r xy yj right. This is the sum of over ij over r over n 1 over n 1 minus t to the n. Right. Right. Yes, this was my mistake. So in the Pochhammer symbol, you start from 0. So from 1 minus a. Thank you. So 1 minus t to the n, and then q to the r, x I, y, j to the power n. Okay. So this is the sum over I and j over r. No, maybe over n rather, n bigger than 1. 1 over n, 1 minus t to the n over 1 minus q to the n. So we summed up the geometric progression. X I, y, j to the power n. And this is the sum over n bigger than 1. 1 minus t to the n over 1 minus q to the n. Pn of x, Pn of y. And then exponentiating back, so to say, we get that this infinite product equals the product over n bigger than 1 of exponentials 1 over n, 1 minus t to the n over 1 minus q to the n, Pn of x, Pn of y. Okay, and well, finally this is the desired right-hand side as 1 week ago. Fine. Now, lemma 2. Pardon me? Oh, sorry. So it's void. The power sum, x1 to the power n plus x2 to the power n plus x3 to the power n, and so on. As you see from here. So the second lemma again was stated and proved a week ago. Let me remind you that for f basis u lambda, well, and v lambda over our vector space of symmetric functions, the following are equivalent. First, that the scalar product u lambda v mu, this qt scalar product, equals delta lambda mu, and second, that the sum over all lambda, u lambda of x, v lambda of y, is this infinite product. So it was proved a week ago. As well. Yes. Yeah. Now, another notation. So we had, if you remember from this whole little business, we had P lambda. We also had dual basis Q lambda, And this q lambda was obtained from some small q lambda that was the product of q lambda I. Yeah, but by some raising operators. And these guys were simpler because they were multiplicative. And now q, unfortunately, is already used up in this deformation. So we'll have to introduce new things g instead of q because they look very similar. So g, yes, n of x, q, and t is defined as the coefficient of y to the n in the product over positive I, t x I y, Pohammer symbol, over x I y, Pohammer symbol. Okay, so in other words, this is the sum over positive n gn of x, q, and t, y to the power n, and g0 is 1. Yes. No, there's just one variable y. It's true that this single variable y later will be in 5 minutes. Oh, sorry. Yeah, I'm sorry. Yeah, sorry. This y will become one of those guys in a moment. Well, here you have infinitely many y's, and they will be viewed, each of them, as this y. Okay. Then let's define, as I just said, g lambda of x qt is the product from I equals 1 to the length of lambda g lambda I of x qt. And our next lemma 3 says that first gn of x qt is equal to the sum over all partitions of size n, z lambda of q t inverse, p lambda of x, and also the scalar product of g lambda x q t and m mu of x is equal to delta lambda mu. So this basis is the dual to the monomial base with respect to this qt scalar product deformed. And again, this was true for the small q guys, and now they're replaced by small g. The proof is immediate, so I still have lemma 1, luckily, fortunately. So we plug in into lemma 1, we plug in y y2 equals y3 equals so on equals 0. It's for A. Now, for B, if we do this, we get this infinite product. Equals the product over J over the sum over positive n, Gn of x q t times yj to the power n, as I promised to Oleg, and this is equal to just because we know that this product is the product over all yj's, right? Is the product over all x's, like here, and then over all y's, right? For when each y is fixed, each j is fixed, you get a product like here, which we already know is this sum. Yes. Mm-hmm. Yes. So we get the sum over lambda, g lambda over x q t times m lambda of y, and we apply lemma 2. Which is just here. Okay, and this equality will be used in a moment. So let me try to keep it on the blackboard. But I will raise lemma 2 now. Pardon me? Yes, and so what? Specialized. But but never mind. We plugged in this to get A, and now to get B, we took product over all y's. So no problem. Yeah. Okay. So in particular, g lambda of x q t form a basis, since it's a dual basis of lambda f, and hence, since it's multiplicative, then g1, g2, g3, and so on are generators. Okay. Now, next lemma 4. Pardon me? That orthogonality is equivalent to decomposition of this product. We decompose this product, and hence we have this orthogonality. Dual basis. So the next lemma concerns a linear operator, well, an endomorphism. E over lambda f and the following statements are equivalent. First, that E is self-adjoint with respect to this Qt deformed scalar product. And second, that if we apply this operator to the infinite product in x, y, but to the x part of variables, then it's the same as if we apply to the y part of variables. And the proof is again simple. So we set E lambda mu is the scalar product of E. Pardon me? That we have two conditions on a linear operator endomorphism of our symmetric function ring. But it's only linear, it's not multiplicative, additive. Okay? So this operator is self-adjoint with respect to this scalar product. Pardon me? Pardon me? Self-adjoint? Yeah, самосопряженный, yes. Right? Okay? Yes. Well, this product is a symmetric function in two sets of variables, in x1, x2, and so on, and y1 and y2, and so on, right? We apply, well, so it's an element of lambda x tensor lambda y, right, over f. And we apply this operator x to the x part of tensor, or to the y part of tensor, and this is the same. And we consider the matrix elements of operator E in, well, it's not quite matrix elements, but it's what is written. Okay, then part A is certainly equivalent to the statement that E lambda mu is E mu lambda. I introduced this new condition, C. Well, if you wish, I'm just explaining the meaning of adjective self-adjoint. Okay. Now, lemma 3b implies that E m lambda is the sum over all mu of E lambda mu G mu, just because G mu is the dual base of M. Okay, and this equality star, which I fortunately didn't erase yet, implies that the product x, y, q, t equals the sum over lambda m lambda of x g lambda of y, or else the sum of m lambda of y g lambda of x, and hence the claim B here, that the action of E in x variables or y variables is the same, is equivalent to the fact that the sum over lambda and mu of E lambda mu g mu of x g lambda of y equals the sum over lambda and mu of E lambda mu g mu of y g lambda of x, and this is clearly equivalent to C. Okay. Yeah. Well, 3b, yeah, this part. It just says that those are dual bases. Since these are dual bases, I know how to compute the scalar product of em lambda with m mu. This implies that em lambda is this sum. Okay. Where? Here? Where? Here. Then everything is in x variables, or in y variables, or in z variables, in any variables you wish. Okay, so well, I'll have to erase something. Unfortunately, last time when we had 8 big blackboards, I just wasted my time chattering, and I have to pay today for this. So, yeah. Well, we just decompose. Well, I know how to apply E to m lambda, and I do this in x variables, or I can do this in y variables and get that. But I know by B that B says that this is the same. This application to x variables, this application to y variables, but I know by condition B that they must be the same. So we have this equality. Yeah, because when I apply E to m, I get this. Okay, so now one more definition, and essentially no more definitions for today. So we have some good luck. Now we have two elements, u and v. They're not bases anymore, but they are just two rational expressions in t and q. And we need v to be not a root of unity. Okay. Then we, yes, not a root of unity. then an endomorphism well, v to the power k is not 1 for any k. In fact, somehow you have a good premonition. MacDonald indeed writes v squared is not 1, but it's a typo, misprint. Maybe I've read him before, I don't know. So an endomorphism of F algebra lambda F omega uv, so it's our deformation of the involution omega, namely in the power sum basis, it is -1 to the power r minus 1, 1 minus u to the r over 1 minus v to the r, pr. Okay? And hence, in the basis, power sum basis, p lambda, we get epsilon lambda, p lambda times the product over all parts of lambda, 1 minus u to lambda I, 1 minus v to lambda I, where epsilon lambda is -1 to the power size of lambda minus length of lambda. Then clearly omega v u, so I swap the order, is omega u v inverse, and omega uu is just our favorite involution omega. Okay? From the winter times. Okay, so the next lemma says, pardon me? The end of what? The definition is just here. It is a set of generators, right? And on these generators, well, we just multiply them by certain scalars. And hence, these generators give an F basis, and in this basis, it's given by this formula. Why? Why? Oh, that's a great idea. So in the end, MacDonald was right. Right. So Cole explains that in our field Q of Q and T, just there are no higher order roots of unity. Absolutely right. There is no cubic root of unity. Okay. Good point. Thank you. Now for u and v, we take our generators Q and T, our variables Q and T. So when we apply this to Gn x q t, then we get En of x. So these Gn of x q t, they deform the complete symmetric functions. If you remember from our early days, this classical involution swapped elementary and complete functions. and Gn deform complete functions. Okay. Next, the scalar product. Well, it's self-adjoint. U v f g is the scalar product of f omega u v g. Next, omega t q f g with respect to deformed scalar product is the same as the scalar product of omega f g, the usual non-deformed involution and non-deformed scalar product. Also, when we apply this involution qt to our product, x, y, q, t, then we get the product over I and j, 1 plus xi, yj, and nothing else. Okay, but when I write this, I mean that in the left-hand side, this omega q t acts on x. And you have here x variables, y variables, but this involution omega acts only on x. Yes, this is our old favorite scalar product. Okay, and by the way, C also implies that the usual Schur functions as lambda and this involution TQ applied to S mu transposed form dual basis. I mean, well, when mu transpose, well, I don't know, maybe I should say lambda transposed. So when lambda here is lambda there, then their product is 1, otherwise 0. Okay, so the proof is straightforward again. So A follows from lemma 3A, and lemma 3A was no, it's not here anymore. Okay, lemma 3A says that Gn over x q t is the sum over all lambda, sum over all lambda of the lambda q p inverse p lambda of x. So it follows from lemma 3a and yeah, and another old fact that En equals the sum over all lambda of size n, E lambda, Z lambda inverse E lambda. Okay. Now B is enough to check for f equals p lambda, g equals p mu by f linearity, and then it's evident. C again the same, just we plug in p power sum functions, and finally D follows from lemma 1, and lemma 1 was the decomposition of this product into infinite sum of power sums again. P lambda of x, P lambda of y with z lambda inverse coefficients. Was from lemma 1 and another old fact. Just again, we check this equality for power sum functions, P lambda and P mu by linearity. Okay, so follows from lemma 1, and another old fact that the product of 1 plus xi yj over all ij is equal to the sum over all lambda, e lambda, z lambda inverse p lambda of x, p lambda of y. Okay, and now we are done with general nonsense, so to say, and we go to Macdonald operators. That's a big. Pardon me. Yes. So we start our study of Macdonald operators, but Macdonald operators, well, as we'll see eventually, they are defined in finitely many variables. So we will need to somehow specialize from what we did to finitely many variables. And we'll need a little preparation for this. So now we'll work with polynomials of n variables, maybe symmetric in n variables. Let's call this lambda n. Lambda n. Lambda n f subscript, because we only the degree is not specified, but only the number of variables is specified. The degree is arbitrary. So we want to define a scalar product there, but the problem is that we had certain bases, and then we defined their dual, but now our bases are not bases in here. We have to impose certain restrictions on the number of variables, and that's what we will do now. So lemma 6 says that g lambda of x q t, but not all of them, but the length of lambda is at most n. form a basis in lambda nf. Okay, and if we know this, then we can consider the dual base or whatever. But just we need some subset of our big base forms a base in this subring of finitely many variables. Okay, so the proof is that if we specialize q equals t equals 0, then, as I said already, Gn is just Hn, and G lambda is H lambda, and then this is the sum over all mu, Kostka numbers k mu lambda of S mu of x. Okay, and now we know that the Schur polynomials in n variables, I mean S lambda, where length of lambda is less than n, they do form a basis in here. So we know just by construction that S lambda of x, when length of lambda is less than or equal to n, form a base in lambda n, and the Kostka matrix is strictly upper triangular, and hence H lambda of x, as length of lambda is at most n, also form a base in lambda n. Okay. Now let's write G lambda of x qt equals the sum over mu b lambda mu of qt mu of x. Yeah. So these are just coefficients of a matrix coefficients, matrix elements of the transition matrix from monomial to G basis. Yeah, something. They are matrix elements of this transition matrix from monomial to G. But we know that this B is some matrix, well, partition, well, maybe not of n, I don't know, partition times partition, with coefficients in F. But we know that this matrix B is regular at the point QT equals 0, 0, and non-degenerate. Invertible. Hence, B lies in GL partition of F. It's some matters, but we know that it can be specialized at some point to an invertible matrix. So its determinant does not vanish identically. Okay, then it's an element of the field which is non-zero. Fine. And now we can define symmetric non-degenerate. Regular means doesn't have a pole there. It lies in the localization of the ring into variables at the maximal ideal 0, 0. Well, it's a rational function that does not have a pole at point 0, 0, at the origin. Yes, so inside F there is a local ring, the localization of polynomials into variables at point 0, 0, at the origin. It lies there. So it's a very non-degenerate bilinear form. With subscript n on lambda and f, such that G lambda forms a dual basis to the monomial basis n mu. Then we can consider the product as before, but only infinitely many variables. Not infinite product, but just in n variables n, x, and n variables y, and q and t. And this will be the sum over all partitions of length at most n, g lambda of x, q, t, times m lambda of y. Okay, and now we are all set, and we can consider Macdonald polynomials, but I will not do this because we only have like 15 minutes. Instead, I will just announce that we will have Macdonald operators, and in fact, it's plural. So there are many Macdonald operators, not just one. Last time, a week ago, I announced one particular operator, but there are many. There are n Macdonald operators in n variables, and that's very good. So we will have commuting Macdonald difference operators. Well, they will be denoted dn1, dn2, and so on, dnn. Well, in n variables, x1, so on, xn. And they will preserve the symmetric functions in those variables. But I just want to say a few general words. This is called integrable system. And I want to say a few general words about what are integrable. Pardon me? Yes. What else could it be? Интегральные системации. I don't know what else could it be. So I want to say some words of apology for integrable systems. Well, you probably study some classical mechanics with Pyatov, don't you? Well, there have ordinary differential equations and evolution along their trajectories. Yeah, so there is a vector field. Whatever V on what on a configuration space X well and the evolution of a mechanical system is along this vector field. Now, well, there's a Hamiltonian approach. To classical mechanics. Well, when the phase space of X is symplectic, say maybe X is cotangent bundle to say to some other half-dimensional manifold M, but not necessarily. It's only an example. And then the vector fields can be very economically encoded in just functions on X, so-called Hamiltonians. You know all this, I presume? Huh? Oleg? Pardon me?
I personally don't know.
And Ira? And then what do you do with Pyatov, I wonder? Pardon me? Okay, then eventually you will. Okay. So, but you know what is symplectic variety, symplectic form? Oh. Well, omega is a non-degenerate closed two form. So d omega is 0. This is clear. The definition is clear. Yeah, there are many things to say about symplectic geometry. It's an infinite subject, yeah. But just what I want to say that since it's not degenerate, it's not degenerate pairing from omega 1 of x to just t1 of x. Okay, it's not degenerate pairing. It also has some, well, integrability property, but anyway, it's non-degenerate, so it defines such an isomorphism. Pardon me, what is T? Tangent bundle is cotangent bundle. Tangent bundle. Okay. So, given a function f, well, a function f, it's called Hamiltonian. We produce a vector field V is just omega applied to df. So df is one form, we apply omega, we obtain a vector field. Okay? And this is one of the key points of say, Arnold paradigm of classical mechanics. Well, it was not invented by Arnold, rather by Hamilton, but Arnold had the nerve to explain to everybody that classical mechanics is just a symplectic geometry, nothing else. And then the Poisson bracket of two functions, f1, f2, is just omega applied to df1, df2. So it's anti-symmetric and satisfies the Jacobi identity with the usual product. So the whole thing is called Poisson structure on the commutative algebra of functions. So there's commutative multiplication and Lie bracket. Together they satisfy the Jacobi and Leibniz rule, and this is called Poisson algebra. Yeah. So this is one form, this is another one form, and you can pair them. Or maybe you can. So omega is a symplectic pairing on the tangent bundle, right? But it's invertible, so you can view it as a pairing on the cotangent bundle as well, and then you apply it to two differentials. Okay?
Сверху поставлен омега df, это векторное поле, а вот снизу поставлен второй аргумент, там получится функция.
Yeah, or you can, this pairing of omega of df1 and df2. Or maybe I should call this omega inverse, I don't know. Okay, so I only want to say that this is homomorphism of Lie algebras. Omega inverse applied to Poisson bracket of f1, f2 is the commutator of vector fields, well, v1, v2. Okay, so if two functions Poisson commute, then the corresponding vector fields will also commute. Okay, and in particular, commutator, just the usual commutator. So in particular, it implies that if indeed, well, say this V we started with, V is omega inverse of df, and f1, f2, and so on commute, well, Poisson commute with f, then f1, f2, and so on are constant along the trajectories of our vector field. So they are conservation laws. Pardon me? I only wanted to say what is an integrable system. And McDonald is a famous example of an integrable system. So I'm still in process of defining integrable systems. Okay? So if dimension of x, it must be necessarily even, and we have n commuting, Poisson commuting functions f, f1, f2, and so on, fn minus 1. Maybe this f should be called f0. Then it is called integrable system. Why? Because then the common level sets of f0 and so on, fn minus 1, generically are just tori, abelian varieties, powers of the circle. Okay? And the evolution along V is just, so to say, straight, well, just a motion along a straight line in S1. In Russian, it's called обмотка Тора. So you have this, and well, you just draw some tangent vector, and then you go along this tangent vector, well, whatever it amounts to. But it's just straight motion along this torus. Okay, and that's the simplest thing could happen in nature. In classical mechanics, nothing could be simpler. Maybe that's not very simple if you see it for the first time in your life, but nothing could be simpler. Say things like many-body problem is a total chaos. It's nothing like this. It's an opposite extreme. So the trajectories are somehow chaotic in the whole phase space. And here you have just this base of integrable system. So there is r to the power n. There's values of these functions. And the fibers are just tori. And the evolution is inside the level set of the whole collection of functions. And inside each torus is just straight motion along some, I don't even know how to say it in English, обмотка Тора. Okay, so this is the most favorable classical mechanical situation. It's called integrable system. And now there is a certain quantization problem in classical quantum mechanics. And in this quantization, you go from this to quantization. of this algebra. And in case, for example, when X is cotangent bundle over something else, then this quantization is just differential operators on M. And to quantize an integrable system is to take this maximal commutative subalgebra in this Poisson algebra and lift it to a maximal commutative subalgebra in this actual associative algebra. So quantum integrable system is a commutative subalgebra in, say, differential operators on M, but a big commutative, a very big, maximal possible, maximal commutative subalgebra. So it's isomorphic to just polynomials in n variables, whatever, z1 and so on, zn. So they are quantizations of those functions. Maybe I should say z0 and so on, zn minus 1. Again, now the time is through. I will say a few more words next time, and then we'll. So now, instead of differential operators, we'll consider difference operators. In this algebra of difference operators, we'll have a maximal possible commutative subalgebra. So difference operators in n variables will have n commuting operators. Certainly, it's something very stupid can be done. Just if you have differential operators in n variables, you can take these variables, or just differentials in these variables. That's something most stupid. But the things that are really interesting, they are some non-trivial operators, but still commuting. There are very famous and archetypical examples like Tode system or Kalager-Moser system or whatever, Ruzinars or whatever. And that's going closer and closer to McDonald. McDonald is common generalization of everything like this. I mean, from McDonald, by degenerations, you can obtain almost all very classical integrable systems.